The concept of minimum description length, (MDL), has played a pivotal role in the field of artificial intelligence over the years. It has served as a fundamental principle that has not only guided the development of AI algorithms, but has also contributed to a deeper understanding of intelligence and data compression. In this historical perspective, we will explore the evolution of MDL, its origins, and its profound impact on AI, highlighting key milestones and the ways it has shaped the field. The roots of MDL can be traced back to information theory, a field pioneered by Claude Shannon in the 1940s. Shannon's work laid the foundation for understanding the fundamental principles of data compression and communication. Shannon introduced the concept of entropy as a measure of uncertainty or information content in a message. This notion of entropy was the first step towards understanding how to encode information efficiently. In the 1960s, the mathematician Andrei Kolmogorov independently developed the concept of algorithmic complexity, which is the measure of the length of the shortest program or algorithm that can generate a particular piece of data. Kolmogorov's work was pivotal in the development of MDL, as it highlighted the idea of encoding data using the simplest possible representation, akin to Occam's razor. The MDL principle was formally introduced by Jorma Rasonen in the early 1970s. Rasonen, a Finnish statistician, proposed that the best way to model data is to find the simplest model that can encode it without loss of information. He coined the term minimum description length to describe this concept. Rasonen's MDL principle is rooted in the idea that the best model is the one that allows us to compress the data most effectively. This idea is closely related to Occam's razor, which suggests that the simplest explanation is often the best. MDL can be thought of as a formalization of Occam's razor in the context of data modeling and model selection. The MDL principle quickly found applications in the emerging field of machine learning. In the late 1970s and early 1980s, researchers began to explore how MDL could be used to guide the selection of models in machine learning tasks. One of the key insights was that MDL could be used to strike a balance between model complexity and data fit. In machine learning, this balance is crucial because overly complex models can overfit the data, while overly simple models may underfit. MDL offered a principled way to find a model that achieves the best trade-off between simplicity and fit. This concept laid the groundwork for the development of various model selection criteria, such as the Akaike Information Criterion, AIC, and the Bayesian Information Criterion, BIC, which are widely used in machine learning and statistics. Another major application of MDL is in data compression. Data compression is the process of representing data in a more efficient way to save storage or transmission bandwidth. MDL provides a theoretical foundation for data compression algorithms by suggesting that the most efficient way to represent data is to find a compact description of it. One of the most famous data compression algorithms that relies on MDL principles is the Lempel-Ziv-Welch (LZW) algorithm, which is used in popular file compression formats like GIF and TIFF. LZW builds a dictionary of frequently occurring patterns in the data and encodes them using shorter codes, effectively compressing the data. MDL has also played a significant role in the field of pattern discovery. Pattern discovery involves finding meaningful and interesting patterns in data. MDL provides a way to measure the complexity of a pattern and determine whether it is a genuine discovery, or simply a result of chance. By using MDL-based techniques, researchers have been able to identify significant patterns in various domains, including bioinformatics, natural language processing, and image analysis. These patterns have practical applications in fields such as genomics, text mining, and computer vision. The impact of MDL on artificial intelligence extends beyond machine learning and data compression. MDL has influenced the way researchers think about intelligence itself. In the quest to create intelligent machines, understanding how to represent and process information efficiently is of paramount importance. MDL has led to the development of algorithms that can automatically discover the structure and regularities in data. For example, unsupervised learning algorithms like principal component analysis, PCA, and independent component analysis, ICA, aim to find the most compact representations of data, which is consistent with MDL principles. MDL has also inspired research in the field of reinforcement learning, where agents learn to make decisions by interacting with an environment. The MDL framework has been used to derive algorithms that find the simplest policies that can solve a given task efficiently. While MDL has had a profound impact on AI, it is not without its challenges and critiques. One major challenge is the computational complexity of MDL-based model selection. Finding the simplest model that fits the data well can be a computationally expensive task, especially for complex data and models. Another critique is that MDL is not always practical for real-world applications. In many cases, the simplest model that fits the data perfectly may be too simplistic to capture the underlying complexity of the real-world phenomena. This trade-off between simplicity and fit is a central issue in MDL-based modeling. Furthermore, MDL is based on the assumption that the true data-generating process is among the models being considered. In practice, it is often challenging to specify a comprehensive set of candidate models, and the true model may not even be in that set. Despite these challenges and critiques, MDL remains a powerful and influential principle in the AI field. Its ability to guide model selection, data compression, and pattern discovery continues to shape the way researchers approach AI problems and has led to numerous practical applications. The MDL principle has a rich historical evolution that spans from its origins in information theory and algorithmic complexity to its profound impact on the field of artificial intelligence. Over the years, MDL has inspired the development of algorithms for model selection, data compression, pattern discovery, and more. MDL's influence on AI can be seen in various domains, from machine learning and data compression to reinforcement learning and unsupervised learning. While it is not without its challenges and critiques, MDL remains a fundamental principle that guides the development of intelligent systems, and has contributed to our understanding of information processing and intelligence itself. As AI continues to advance, the minimum description length principle is likely to remain a central concept, providing valuable insights and practical tools for researchers and practitioners in the field. It reminds us that simplicity and efficiency are not just desirable qualities, but are essential principles for achieving intelligence in machines.